Okay, so let's wait for some time. Someone join. Okay, so let's wait for 3-4 more minutes. Let the others join, then we will get started.
Good evening, sir.
Good evening, good evening. Just waiting for some other people to join, then we will get started.
Okay, sir.
So in last lecture, I discussed about various phases of compiler, its applications and other aspects. This week is mostly about lexical analyzer. So lexical analysis is the first phase of compiler design where we take input from user and scan one by one. And after scanning the input in lexical analysis, we go for next steps like parsing, semantic analysis, and other phases. So in week 2, the thing covered is mostly about this lexical analysis phase, and the basic of this, how a compiler does this lexical analysis, that is using DFA or NFA, so finite automata. So in today's lecture I will just first brief about the concepts, what is taught in this week, and then we will go through previous year questions and also some questions about DFA and NFA and how to convert. If time will allow us, I will show an example on how to convert NFA to DFA. So let's wait 2 more minutes if any other is joining. Otherwise, I will start the lecture at 7:03. Just wait for 2 more minutes. So in last lecture, if there is any doubt, then till that time you can ask in chat. So okay, I think I should get started, and then those who will join late, I will just brief them. So in this week, the major thing which was covered was lexical analysis. In this, the first thing, the topics they have covered, the concepts they have covered is roles, and then tokens, patterns, and lexemes. Then lexical errors and recovery, then specification, recognition, and then finite automata. So going one by one, I'm just revising the concept first as we have a lot of time. So the role of lexical analysis to uh, take the source program and retrieve tokens from here so that it can run with the parser hand by hand. So as an input you can see here uh, there is source program as input, then we feed it to lexical analyzer, then uh, it generates the token, and this token is provided to parser immediately, and it actually requests for the next token, and then uh, after parsing, the output of parsing is uh, given to the semantic analysis phase. So and all of these phases are actually connected to symbol table. So this way lexical analysis works. So major thing what we should remember is that it is the first phase which interacts with the user directly. So we will take a source program, we will provide it to computer or any language, means any machine. So first it will go through lexical analysis phase where it will take source program, and it will go letter by letter. It will take all the means what is written in this source program letter by letter. It will scan it, and then it will actually analyze it and create token based upon how it is coded, and this token is simultaneously given to the parser. So this is one thing which is taught in lecture, how we why we separate lexical analysis and parsing phase, because we can take it as a combined module. So first is simplicity in design. So it will make us differentiate between the basic works, what we can say. So like if we will combine these two, uh, that that will result in a complex design that is taught, and then improving compiler efficiency. So if we have separate lexical analyzer, then we will get uh, tokens in means a more efficient manner, and also enhancing the compiler portability. So if we want to port our code from one platform to another platform, then if they will want a single kind of token and different kind of parsing, that is also feasible in this case. So I'm just briefing it. If you want to learn more about it, you can go through the lectures again. So next thing that was covered is tokens, patterns, and lexemes. So token, what is a token? Token is actually a pair. In this we have a token name and an optional token value. So in later example I will show that is given in this slide only, and then there is a pattern. Pattern is actually a description of the form that the lexemes of a token may take. So lexeme is actually a sequence of character in that source program, and based upon that lexeme, uh, yeah, it is example is actually given in that lecture only. So I will show an example after covering these slides of the lecture. That will clear your doubt if there is any. So if there is lexeme, you can take instruction and show the exact tokens. Yes, I will show. So lexeme is a sequence of character given in that program, and the pattern is actually is a descriptive form, what we can replace with the lexemes. So like if there is a token, if the informal description means what it will contain. It will contain the characters I and F, and the sample lexeme we will use it is actually the is if condition that is used in C program. Okay, if we will just take example in case of C programming only. So if we will see these characters, so what if will contain it will have I and then F. So if we will have a machine, um, or you can say compiler, which has a token named if, so first it will go through any kind of string, uh, or we can say it will go through program letter by letter. If it will get a letter I, then it will search for the next letter. If that we will get F from there, then uh, it will say that yes, I have got lexeme if. So it will get lexeme if, and the lexeme, the token attached to that lexeme will be if token. Okay, so let me take an example. Okay, so let's consider one case. If we are given some program, and in that C program you can say if there is a condition like if a is greater than 0. So if we will provide it to compiler, so compiler will just scan what we are uh, providing it as input. So it will scan one by one. Okay, so there will be I. So it will scan I, then F, then this symbol, then A, then 0, then close bracket. So this will happen first. Then compiler will uh, search for its finite automata what it is using. So using that finite automata, it will just scan it for the token. So first it will get I, then it will search for the next one. If it will get F, then it will create if lexeme. Okay, so we have got if lexeme. If anything else, then that will be that will have some other means sequence to follow in that finite automata machine. Okay, so it has got to the final state, and it got this lexeme if. So it has got lexeme if, and corresponding token what the lexeme if is recognized by compiler now. Now what we will get, we will oh, sorry, yeah. So now lexeme if is recognized, then next step, compiler will search for the corresponding token which lexeme if is assigned. So that is if token. Okay, so in this way we can say that in a compiler program any token is recognized. Okay, so Sasikant, this is what you, I think what you were asking. So likewise there is else. Let me say it again. So Is my screen visible? Can anyone confirm, please?
No, sir, no, sir.
Is it visible example slide?
No, sir.
Okay,
Now it is not screen is not shared.
okay. Thanks. Yeah. Sorry, there is a technical glitch. Okay, I think it's visible now.
Now it's okay, sir.
Okay, thanks. Uh, so as I have shown how we will recognize the token, if in same manner this else can be recognized if there is any comparison operator. So there will be sample lexemes, and based upon sample lexemes the compiler will generate this token comparison. Same for id, number, and the literal. Okay, so like literal will be always surrounded by these quotes, double quotes. Okay, for example that is given in this ppt is equal to mc square. So for this first it will go one by one, it will scan uh, the equation. So first it has got this e, so it will return uh, e is identifier, so it will return id, then pointer to symbol table entry for e. Okay, that is actually a token. Then there is this this assign operator that will be returned. Then there is m, so it is id, and it will go to the symbol table entry for m. Then for multiply operator, multiplication, then there is okay, so then there is c, that is also identifier. Then there is double asterisk sign, that is actually for exponential operator. Then there is number. So in this way uh, all the strings, all these things will be provided a token. Okay, there is okay. Okay, now again joined. Okay, so moving forward, then there is some lexical errors. How it will be recognized? If there is something scanned which is not in the means dictionary of the language, means something that cannot be recognized by lexical analyzer for the given language, then that will fall in this lexical error case. Okay, like in this example what I have shown, that if there is fi instead of if, then there will be some error. It will not be recognized as if, and it is not also any kind of keyword that is there in the language, then it will show some kind of error here. Then there is uh, a case when uh, there is some pattern which cannot be recognized, like you can see here d is equal to 2r is actually looking good for means in day-to-day life, but for programming language 2r is actually if you will just consider the case of C language, then that is not feasible. If we will write 2r, that will not be an identifier, that will also cannot be categorized into any integer, because identifier should start from letter, means there should be any alphabet, and then there may be some integer or underscore, so it should start from any underscore or any kind of means letter, but it is starting from 2, and then there is not any uh, operation in between r and 2, so it is actually not, it cannot be classified as any kind of identifier here, and it is not also a integer value, so that's why it will provide some error. If in this case if there is 2 multiply by r is written, then that will, there will not be any error, or if there is r2 will be written, then there that will not show any error. So what I am telling, if there is written as this 2 then some operation then r, then there will be no error, and if it is written r2, then there will be no error, as r2 will be considered as identifier because it is starting from r, not any number, and here it will see that there is a multiplication sign between these two, so there is operation between number and the letter, so there will also not be an error, but in this case there will be error. So if there is a pattern, if there is any symbol which cannot be recognized by lexical analyzer, then there will be surely an error that will be considered as lexical error. So if there are some errors, then there must be some recovery uh, procedures. So in error recovery, the basic mode is actually panic mode. So uh, what we do is that we just ignore the successive characters, uh, and then we reach to the well formed token. So if there is some character written between a valid token, then that will be ignored, or there are multiple other things, like we can actually sorry, we can actually delete one character from remaining input if that is creating some problem to the that is creating some problem to recognize the token, and we can also insert a missing character. That depends on compiler by compiler, and also we can replace a character by another character, we can take transpose of adjacent characters, so that are different things that we can do for error recovery, and that totally depends upon how compiler program is written. So if there is not any way, what it means by well-formed token, well-formed token means the token which can be recognized by the compiler. So like there is if token is there, so if we are searching in program that there is, just consider this last case, transpose of two adjacent characters, or just consider this case, displays a character by another character. So if there is fi is given instead of if, so what we are telling, that if it is not forming a token, then we can either we can remove we can replace them with some different characters. So if I replace this f with I and I with f, then it will create a well formed token. Okay, so the ultimate aim for error recovery is to just create the token which the compiler can recognize for later phases. So in that way error recovery can be done, but that depends upon compiler program, I already told, because if there is no way to, so it means token for which specification already defined. uh, haven't got what you are telling, just a second. Means token for which specification already defined. Yes, that and that also depends upon the compiler program what we are using. Okay, so it is match, then okay, otherwise yes, that's why error recovery is there. So if there is means if these five are the possible cases what we can do with any kind of compiler. There may be another kind of recovery which new compilers can do, and uh, means if that is not written in if any kind of these suggestions are not programmed in the compiler program, then that will not happen, error recovery will not happen. But if anything is there in the compiler, then it will be done. Means if there is procedure written in the compiler program to replace a character by another character, so if it will not get satisfiable token, then it will replace it. Otherwise if it is not given in the program, then it will not do, I think. Okay, then another thing is input buffering is actually done to look ahead some symbols to decide about which token to be returned. Okay, so like there is a asterisk symbol, that is multiplication, then there is double asterisk, that is for power symbol. So if there is a buffer, then it will go to, means scan the next symbol also, look ahead one symbol. Otherwise it will not do like that, it will just if there is no buffer, then it will just see C and then this asterisk, and then there is again an operation that will be, if that means if that is that maybe means result in some error. Okay, uh, then the specification of tokens. So there are regular expressions uh, for regular languages, and based upon this these regular expressions we actually create the finite automata, and that finite automata is given the input from the user, which is the input to the compiler actually, and that finite automata creates the token as output, means tells the compiler about the tokens, whether the scanned letter is actually a keyword or not, or anything it is digit or not. That will be totally done by the help of that uh, finite automata, and that finite automata is actually based upon some regular expressions to follow. Then there is regular expression. So epsilon is a regular expression denoting the language epsilon, so that is empty string actually. Epsilon is there to just point out the empty string. Then if a is the symbol in this language, uh, then in this set, then a is the regular expression, then language of a will contain a only. Similarly, if there is r and then there is oblique symbol, so it actually shows lr union ls. So if there is some language r, there is some language s, then LR union S or R or S regular expression will denote the strings. All those are from LR and also from LS, means either present in LR or in LS. Then there is RS, so that is actually for concatenating. So it will concatenate each of the string that is given in R to S, and the first string will be from R, and it is written as LRLS, and then it will append the next one from S. Then there is R star, that tells about, means the set containing 0 or more string. Then there is R, that is regular expression for language LR. Then there are some definitions. These are there that for writing in a convenient way and making the means regular expressions less complex to understand. So like if we are telling letters, then letters underscore uh, are actually to show these things, A or B or up to Z or any letter or underscore. Then if we are writing digit, it denotes 0 up to 9. If there is ID, then ID is actually, or identifier is actually letter, given letter or digit, and then star, means it is telling there will be some letter or underscore, and then there will be 0 or more than 0 occurrences of letter, underscore or digit, that will be specified as or recognized as ID token by the compiler. Okay, now coming to next part, there are extensions. So if we are writing plus, then we are telling that there will be at least one instance. 0 of one instance will be given this by this R, then question mark symbol. Then there is character classes. We can write it like this. So like here we have written the previous one using this A to Z, and underscore, and within this character class symbol, then 0 to 9, then likewise. Just a second. So these are some examples. So I would like to show with the help of some other examples. So let me share the screen. So first case is we have the examples with the 0 or 1. So any language has these alphabets 0 and 1. Now if we are writing something like 0 or 1 then star, then what will it show? It will show all binary strings including the empty string. So this symbol is there for 0 or more than 0 occurrences, and this is for 0 or 1. Okay, so in if we will generate strings using this language, what we will get, either it should be any empty string if any of 0 or 1 is not there, or we can generate 0 from here, we can generate 1 from here, 0 or 1 occurrence, or we can have different more than one occurrence. So different combinations of 0 and 1. So 0 1, or there will be 0 0, 1 1 or 1 0, and likewise we can generate these kind of strings. Okay, so this is the first case. Then there is a second one, 0 or 1, and then 0 or 1 star or asterisk. So what it will, so it is written all non-empty binary strings. So from here what we can infer is there the first letter of the string starting with this language will have any of this 0 or 1. So either we have 0 or 1 as a first first character, then we have 0 or more than 0 occurrences of 0 or 1. So that will be, if that is empty, then that will be 0 only. If there is any 0 or 1, then 0 0 0 1, and in this case 1 0 1 1, and likewise. Okay, so 0 0 1 or 1 1 0, likewise that will be generated. So all non-empty binary strings, so there will be no empty string, as the first letter is having 0 or 1 value, and then any occurrence of 0 or 1. Then in third case it is given 0, then 0 or 1 star, then 0. So what it will show, it will actually show that uh, there will, the string that will start with 0 and end with also 0, and the binary string will have length of at least 2, because this will be there and this will be there. Rest 0 or 1, that will be optional thing, because there is a asterisk over there, so that may happen, that may not happen. So we will have 0 0 if it is empty, then if there is one occurrence, then 0 0 0 or 0 1 0. If there is more than one occurrence, then there will be 0 0, and in between 0 1 0 0 1 0 0 0 1 1 0 0 0 0, likewise. Okay, so oh, there is again network connectivity. There is some network issue. I'm trying to reconnect. Okay, just comment. Am I audible now? Hello, am I audible? Okay, thank you. So I was telling about this combination. Then likewise, then again, uh, there are multiple other examples given in the slide. So just quickly going through this: 0 or 1 asterisk, then 0 or 1, then 0 or 1, and 0 or 1. So what it is telling, we should have 1 2 3 and 4 characters, at least 4 character strings, and that uh, in this the second, at least there is third last character is always 0. Okay, so last, then second last, then third last. mm, Not third last, it should be fourth last, so it will be 0. And then, okay, what is written, what type of string will be made of this input? uh, okay, just let me complete this. I am coming to you. So it will generate 0 or 1, then 0, then there will be 0 or 1, anything, or 0 or 1, anything, then 0 or 1, and here 1 0 1 1 1, and likewise. So your question is A, then A or B, sorry, A B, then 1 star. Okay. First thing is this should be there in the language. These alphabets should be there in the language. So language should contain A B, then 1. Then we have to just provide this. A should be there if that is this your empty string. Otherwise A B, then A1, A B, A11, or A1 AB, and likewise. What is complex in this? That is so simple. So you have to just apply the operations that are discussed. So for AB or 1, there is a asterisk sign, so that may happen, that may not happen. So there will be at least means 0 occurrences of this, and that the string will start from A, and then we'll have any occurrences of AB or 1. That's it. Any doubt? If I am wrong, then anyone can comment. So likewise, uh, now going to the other slides. So these were some examples. Then there is also an example for floating point numbers, then that it may have first sign, or there will be no sign, then there will be a single digit, and then multiple digits may occur or not. So at least there should be one digit after this plus minus, or there will be no sign, then dot, then there will be some digit, or there will be nothing, and then exponential e, then its power plus minus, or there will be nothing, and then there is digit or set of digits. So this is the recognition of token. So starting point is the language grammar to understand the token. So we will go through the grammar, and then we will means take and scan the whole input string, and then we will search to the grammar whether this token is recognized or not for that grammar. Like, so again, that is for recognition of token. It is discussed thoroughly in the lectures. Then there is transition diagram for relop. So it is like finite automata only. If there is a start state, then there is zero. Then if it will get less than, then it will go to first state. Then if it will get equal, then it will go to the final state 2, and it will return less equal relop as a token. Similarly, for this less than or greater than means that is not equal, then there is, if it is other, then there is less than. Similarly for equal, similarly for greater than symbol. So this is something automata machine does. So next is the transition diagram, how it actually works. So these all things are discussed in the lecture, that how this transition diagram based lexical analyzer works. So for the previous example, what we have shown in this transition diagram, that is written here. So if it generates a relop, and it's in switch statement, we can see that if it is equal to less, then we will go to state 1. If less then equal to, then we will go to 5. Likewise, we means after all the statements, we will get this fail statement. If it is not there, then lexeme is not a relop. Then there is finite automata. So for finite automata, what I have earlier told also, that we are given some regular expressions, and those are actually specifications for the machine, and finite automata is just the implementation of the same. So it consists of this alphabet character, which is shown by this summation symbol. Then there is some set of state S, then there is start state, then there is accepting states, and transition is like state, then we will give some input, then another state. Like from state S1, if we are given input A, we will go to S2. So if it is followed for overall string, means if it is accepting the state and going to the final state, then it will accept it, otherwise it will reject, and if there is no transition possible, then also it will reject it. So these are state diagrams. What finite automata uses, there is a state, then there is a starting state, which is shown by circle, then a symbol, then there is accepting state, then there is transition, how transition is done or shown. So it is a simple example. What it is showing is that finite automata which accept only one. So likewise any number of 1, then 0, so If it will get 1, it will go through this state again, and then if it will get 0, it will just go to final state and accept the string. So these are some examples. There are silent moves also. Means we can change between among the states without any input, without reading input. So these are two kind of automatas. uh, there is, in some books you will get three variants: deterministic, non-deterministic, and epsilon non-deterministic. But in our case we are just differentiating in these two only. So DFA and NFA, deterministic finite automata and non-deterministic finite automata. So in DFA there is one transition per input state and no epsilon moves, and in NFA there will be multiple transitions in one input given states, and that can have epsilon moves, can have also epsilon moves. And finite automata will have always finite memory and need only to encode the current state. So in DFA there will be only one path completely determined by input, but NFA can choose whether to make epsilon moves also, and multiple transition from single input we can take. Then acceptance of NFA, if we get to final state, it will be accepted, and both are similarly powerful. Okay, so both can recognize same set of languages or regular languages, and DFAs are easier to implement, so there are no choices to consider. That's why these are easier to means implement. We are given input, and based upon that we will generate the output. Then there is NFA versus DFA. DFA can be exponentially larger than NFA, and NFA can be simpler than DFA for a given language. This is how we can convert lexical specification to the DFA. We will go through this lexical specification, then we will generate this regular expression. From there we will go to this NFA, then NFA. From NFA we will generate DFA and table driven implementation of DFA. So these are some ways to convert NFA to DFA. Now I will go through some examples based upon these problems one by one. Okay, so I am sharing this. So I will take three examples. In first I will generate a DFA, then in second I will generate a NFA, and then I will take an example to convert that an NFA to DFA. So before that I think I should go through some examples, some previous year questions, then we will go through the examples. So let's go through one by one. So please use chat to answer these questions. If there is some doubt we will discuss. So when the lexical analyzer reads the source code, it scans the code line by line, word by word, letter by letter, or whole at a time. What should be the answer? Just write and chat. C. Any other answer? Yeah, everyone please join this. So you are correct. C is the right answer. Whenever we get this program, we scan letter by letter. If there is some pattern to follow by the letters, then the finite automata which the means it is using actually, that actually scans for the next character, and if that next character is creating some token, then that will be good, otherwise it creates just identifier token. Now coming to the next one. The regular expression for a string over alphabet set 0 1 in which 0 is always followed by at least two ones, that is 1 1, is. Any other answers? A, B, C, A. What is C? Not possible to create such a regular expression. No, no, that is not correct. You can create. So 0 1 1 should be there. That is for sure. So YB and YA. Let's go through it and try method. If we generate the strings from A and if we generate a string from B, so what will happen if we will select this 1 star, then 0 1 1 star, what it will generate? 1 0 1 1 0 1 1 1, and then 1 0 1 1 1 0 1 1. So will it be possible? Here also you can see 0 is always followed by at least two ones, but it will not happen here. Oh, sorry, that is happening, I think. So let's clear all the things. Answer is A. Okay, so answer is A. We are just, let's just create the strings. So 1 0 1 1, or there will be 0 1 1, or there will be empty string. So what it is telling that if there is 0, then there should be any 2 1 1. But if you will see, it may have it will contain this epsilon, then 1, then 1011 or 011 or 1011011 or 11011 likewise. This is for this A. If you will take B, what it will create? Empty string 1011, then 1011, okay. So then 1011, then there should be 1011011, 11011. So I think my A and B both are getting correct. Can anyone comment on this point? Answer is A. The answer given is we can't create all possible strings with B, as 1011 11011 is also accepted produced by A. Okay, yeah, right, correct Siddharth. So thanks for the help. So answer is A. Why? Just say this example 1011 this can be produced by A but not by B. If we will, and here you can see the 0 is having 4 times this 1 and 2 times 1 so at least 2 ones should be there. But if we want to generate with this second expressions, so 1011 will be there, then if we will again generate again go through this 011, then again we cannot generate this. And if we will take this one, generate one only, then also sorry, 11011 can be generated, but this cannot be generated, which actually will be there in this language. It should be there in the language which it is stating. So that's why A is correct. C is surely not correct. We can create, and D is not. So A is the answer. There is a possibility of empty string in both cases. Yes, there will be. The empty string will be generated in both cases, because the empty string uh, there is 0 or 1 occurrences, sorry, 0 or more than 0 occurrences, so it is over there. So empty can be generated by this also, and empty will be there for this language also, because if there will be no 0, we don't need 1 to 1 follow them. Okay, so answer is A. Coming to the next one, there is a diagram. If it is not clearly shown, I can draw it again. 1, then 1, then there is, oh sorry, what I'm doing, there is final state 0, then 1, then 1. This is a diagram. The question always is specified. Yes, and at least is there. So that uh, okay. So coming to this one, what should be the answer? Look, we are discussing here, so if I am not getting anything, or if I am going wrongly, so you can comment. It is open for all discussion. From my side, I will try to bring right things, but if there is some doubt from my side, or I am conveying anything wrong, I am not clear in any concept, you can just comment. So yeah, coming to third question, please. Siddharth's answer is B. Any other answers? Anyone is commenting? Everyone, please comment. Just try. It's very simple. If you see, uh, if you will go through this input state to another state, we will get 1. Then to another state, we will get 1. Then there are multiple zeros. We can, if we will get 0, we will be there in the final state. It will be accepted. But if there is any 1, then there is no state here. So uh, we can say that strings starting with 1 1 and then ending with any number of zeros. So strings starting with 1 1 and ending with any number of zeros. It may be 0 or 1 or any number of zeros. So that is one thing. So if we will go through this option A, so 1 1, then 0 will again put it to this state, so it will be in final state, it will be accepted. Then there is 1 1 1 1, so what will happen? 1 1, then 1, there is no state defined as a final state after getting two ones, so that is the correct answer for this. Then there is 1 1 0 0 0 0, so after 1 1 multiple times 1 0 will come, then again 0 will come likewise, so it will also be accepted and this will also be accepted. So answer is B. Okay, so next one, the number of possible transition from a state in NFA is, just comment for this one. A, right. Okay, there is A. That is theoretical question totally. Hmm. Then the next one, it is also a very theoretical one. Which one is more powerful? B. Any other answer? A, B. Look, uh, in theory, I have revised also that both NFA DFA works on finite set of language or finite set of characters. So both are actually equally powerful. We can generate same strings from both of them. So C is the correct answer. Okay, what we can generate with DFA, we can also generate with NFA.
Sir, but the reverse is not true, na? If there is something that can be generated by NFA, it is not necessary that it can be generated by DFA also. Since
Yes,
that's a finite automata.
yes, yes, yes. But we can generate the languages, means strings from NFA and DFA, and in theory, if you will see, there is you will get that both are equally powerful. So if there is any other uh, comment about this,
No, sir.
okay, I will get back to you in next week lecture if there is any other uh, comment about this answer, because in everywhere you will see, you will get this answer only, that both are equally powerful. So I am marking it. I will again discuss in next class. Okay, for now onwards it is C. I will discuss it again. Okay, for 6-1, regular expression cannot represent any language, part of language, constituent strings of a language, or none of the other options. C. Yeah, that is fine. Uh, it actually represents a constituent strings of the language. Then seventh one, finite automata is an implementation of part of a regular expression, any grammar or regular expression, or none of these. Yes, regular expressions. I have already told in slides. Yes. Which is easier to implement? Easier to implement. Not B. In slides it is written DFA is easier to implement because we have actually given a single input and corresponding output, and we have to just generate for a given sequence. So we actually know what to generate and which for which input. Mm, in slides it was written just refer to slide number 35. uh, for last two questions, I'm just referring what is taught in course. So uh, just refer this slide. uh, NFAs and DFAs recognize the same set of languages, that is regular languages, and DFAs are easier to implement. There are no choices to consider. So I am just answering based upon this difference. Okay. It is answered, I think. Yeah. So ninth one. Just answer the ninth one. Regular expression 0 or 1 star 0 0 will accept all the strings. Any answers for this one? Am I audible? Yeah. So please answer this one. Accept all strings divisible by 2. Any other answer? See, divisible by 2 and minimum length 2. How? Just go through binary values, then answer it. What it will generate, the convert it into decimal. If you are not getting actually the question, what the question is telling, just generate the strings and then convert it into decimal and then just try. So what it will generate? It will generate 0 0 or 0 0 0 or 1 0 0 or 0 1 0 0 or 1 1 0 0, likewise. Okay, so it will be 0 0 4 4, that will be 4 plus 8 12, or 1 0 0 0, that is also possible, 16. So what we are getting? Anything divisible by 4. Okay, now two options are remained. What is the minimum length? Because this is the optional one, it may be there, it may not be there. Minimum length will be 2, so answer will be B. Okay, any doubt? Okay, so next one. It's very simple one. B, right. Okay, lexeme is not any sequence of character, it is actually a sequence of character that defines a token. It is not same as token, and it is related to token. Okay, so this is something I think that is not covered. Output of a tool lex is actually, if anyone knows, can comment. What will be the answer? Yes, a C program. Okay, output of the lex tool is C program. So these were some questions. Now coming to the, I am giving you 2 minutes. If there is doubt in any question, just comment. Otherwise, I will move forward.
Sir, can you give a clear explanation on the corresponding 14th question in assignment 2? Because
Corresponding,
assignment 2 actually it is completed and evaluated, but I need a clarity on the 14th question of assignment 2.
14th question in this year's assignment.
Last week, second week.
Means in current run.
Yes, sir. The topic which you are discussing today, in that week only that particular assignment was given.
Uh, we are not allowed to discuss this year's assignment. So uh, you just write it on discussion forum. What they will tell,
Okay.
we will follow. So explain it. Binary string in which one is always followed by at least a single zero. Prasanna, please mute your mic. Uh, Binary string in which one is always followed by at least a single zero. So one should be there. Yeah, one should be there, and then one is always followed. One is always followed by a single zero. No, no, no. That is there in PPT, I think. One is always followed by single zero. So you are telling about 10 should have epsilon or 0 or 10 100. Yeah, yeah, fine. So 10 star, then whole star. So what it will generate? Uh, First epsilon, then 10. Sorry, no, 0 should be there. Plus 0 should be there. So you can write it like, I think, star or 0. Okay. So 0 will be there, or 10, that will generate this epsilon, and 0 will be generated from this. Then there will be 1. Mm, 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 mm. No, 1, then If we are taking 1 0, it will also generate 1 also. I think it can generate 1 also. That's a good question. So if we are just taking base of this 1 0 star whole star or 0, then we will also take 1 0 in consideration, but it will generate 1 0 also. So 1 0 star, then 0 star. I think that is something we want. If we will generate this, we can generate epsilon, we can generate 0, we can generate 1 0. Yes, I think this is the right answer. You can generate all things from here. If I am wrong, you can comment. 1 0 whole star, then 0 star Revanth. At least a single 0. So it can go through multiple zeros, and single 0 is there with 1. I think that's perfect. Any doubt? Revanth, have you got your answer? Okay. So the previous year questions are done. So I will go through one examples for DFA, then NFA, and then converting NFA to DFA, as we have a little time left. So the question is, we have to draw. No, before it, I have I think another question on lexical analysis part. You can try this. Just answer this one. What are the correct answers? Just try this for 3 minutes. It's 8:27, 28. Just 2 minutes. At 8:30 I will disclose the answers. Take 2 minutes and just solve it. It's a very clearly written. You can try, and more than one answers may be correct. Anyone got the answer? Not all. Just to uh, there are two options correct. Now choose which two are correct, just to help. It is looking that each of the option is correct. That's why I have taken this question. Just read it clearly. You will get option 3 is correct, right? And 1 and 2. What about 1 and 2? Let's see. uh, we are given this word. Okay, now how word can generate the lexical entries, means how it can derive. If we want to generate, I am going from 3 to, yes, 2 is also correct, 3 to 1. So if we want to generate this one, how word can go? First is letter. So we have three options for letter. We have letter, or later than char pair, or later than int pair. So if we go with char pair, it will generate char pair, then later and later, or two letters at a time. But if we will go with int pair, it will generate integer integer, or int pair integer integer. So if we will go through this derivation, letter then int pair, what it will generate? It will generate, or it will derive this, it can go to this int pair will get this integer integer, or int pair integer integer, but we have integer integer, so integer integer. Now letter can take any value from here, so it can take C, and integer can take any value from here, it can take 4 from here. So C44 is a correct one. Now coming to the next one, that is pix. So word can also derive like this, letter and char pair. Okay, so what char pair can derive? Char pair can derive char pair, then later, then later. So later char pair, later, then later, then again char pair can derive later and later. So we have now later, 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 letter, and letter. So we have 5 letters. One letter can take P, I, C, K, S. So second is correct. If we want to generate peak from here, can we generate? If we will go through this letter and char pair, we can generate. The first thing is correct, that we will go through this way only, because one letter cannot generate it. We have to go to letter and char pair, and in pair can also not generate this peak, because next one is character. So char pair, from char pair we can generate either two letters, or char pair then two letters. So it, what we will get, either a string having 3 characters or 5 characters. So 4 character string we cannot generate from here. So answer is 2 and 3. Okay, any doubt? Think it's clear. So okay, coming to DFA question. Draw a DFA for the language accepting strings ending with 0 over input alphabet 0 and 1. Okay, so what we have to generate is a DFA from it. So first thing what we will do, we have to generate the regular expression for this case. What will be the regular expression? The it should end with, ending with 0 1. Okay, 0 1. So At the end we have 0 1, and before it we can have any number of 0 or 1s. So this is regular expression. So there is one rule for DFA. If we have length of substring is 2, means n, then the states will be n plus 1. So here the substring which will always be there is 2. So the number of states will be equal to 2 plus 1, that is 3. Now let's say we have state A, B, and there is some final state C. A is the initial state and C is the final state. Now we have to just provide the transition between these states. So from A means from starting or initialization, if we will get 0 and if we will get 1, what we will do? If we will get 0, then we should transit to another state, and if we will get 1, we should go to final state. Okay, that is clear. Means the string should end with 0 or 1. So if there is 0, we will go to B, and 1 we will go to final state. Now if there is any 0, if we will get any 1, then what will happen? If we will in starting we will get any 1, then we don't have to do anything, we will be there in A only. Means we will search for 0 1. Now if we got 0, we will search for 1. If we will get 0, then we will be in the same state only, we will search for 1 again. Then if we are at final state, we have got 0 1. If we will get any 0 again, then we will search for 1, and if we will get any 1, then we will search for 0 1. So we have to go logically. So again I am telling, we have to create the string which we can understand it in this way only also. So we have substring of 2 characters, so we have to just create a machine which can accept these 2 characters. Okay, so we have 3 states, we have to accept 0 1. So 0 then 1, and this is final state, this is initial state. So now for the corner cases, if there is any 1 before 0, we will search for. If there is 1, we have to search for 0 1. If we have 1, we have 0, we have to search for 1. So 1 we have to search for 0 1. Then if we have 0, we have to search for 1 only. So if we will get 0, we will be there only. If we have 0 1, we will again search for 0 1. So if we will get 0 from here, we will search for 1. If we will get 1, we will search for 0 1. So in this way we can create this DFA. So the string, what strings it can create? It can create 0 1, 1 0 1, 0 1 0 1, and so on. Okay, so this is how can we create a DFA. Now for an example of this NFA, we have a set of 5 things. So we define it as the Q, then alphabet, then transition function, then this is the initial state, then there is the final states, set of final states. So this is actually finite number of states this is a non-empty set of symbols. We also tell them alphabets. This is actually transition function. This is initial state. It belongs to Q only, means finite set of states only. Then this is set of final states, which is actually a proper subset of this. A subset of this states only. Okay, just a second. So consider this question. We are given transition functions delta of a we can also go to e. Yeah, Menka, please tell. Please write in comment. Then there is b equal to c. C on C goes to D, then E on B goes to F, then F on C goes to E. So from here we should create a transition table. Okay, so here we should have states or alphabets, then there are letters B and C. So we have A, B, C, D, E and F states. From A, if we will get A as input, we will go to B or E. On B we don't have any entry, C I don't have any entry. From B, on B we will go to C, no other entries. C on C we will go to D, no other entries. D we don't have any entries. E on B goes to F, F on C goes to E, and D and F are given as final states. Okay, in this question only. So how we will create it? It's very simple. You have to just see the transition table and just create the transition. So, and this is the initial state. So initial state we are given. From here we have, on A we have to go to B and E. On A we will go to B and we will go to E. Sorry, on A. Then from B on C we will go to state C, and from A on B, E on B we will go to F, and F is the final state. From C on D we will go to D, and D is the final state, and from F on C we will return to E. So this way we can create an FA from a given transition functions. Okay, these are very simple examples, as our work is just to know how the things work. So now the In last 15 minutes I will just go through a simple example of how to convert NFA to DFA. So to NFA to DFA, just consider this machine. We are given an NFA AB, then on B it goes to Q1, on A it goes to the final state Q2. Okay. Now we will just create a, let's create a transition table from it. Let's say it is T. So from T, what we will get in transition table, we will have this states, then alphabets. So alphabets are here A and B, and we have three states: Q1, then Q0, then Q1, then Q2. That is the final states. So in final state, okay, so Q0 on A just goes to Q0 only, and on B it goes to Q0 and also on Q1. Q1 on A goes to Q2. Oh, sorry, that is B on A. Now we can think it in that way also. That is nothing on Q2, and Q2 doesn't go anywhere. So that is the transition table formed for NFA. Now coming to the next part, we are given some transition table like this. Now we have to convert, we have to create the different states from this given thing, given transition table. So we will create new states. So we will just generate a different transition table with the help of this only. So state and this A and B. So from Q0 we went to Q0, and where there are more than one entry, we will consider them as a single state. So Q0 Q1 is now a state. This is one thing. Now the transitions from Q0 Q1 will be the all the transitions which are made by Q1 and Q0. So we will go one by one, means from Q0 we went to Q0 Q1. Now we will see the transition of Q0 Q1. Okay, so Q0 Q1 on A will go to which state? So we have to go to this table. In this table, uh, in this table T, we will go through this Q0 and Q1. Q0 on A goes to Q0 only, and Q1 doesn't have any entry, means empty state. So we will take set means both of these entries, and we will create the different states. So here we have Q0 and empty string, so it will result in Q0 only. And for Q0 Q1 on B, so Q0 on B goes to Q0 Q1, and Q1 goes to Q2. So the set will contain Q0 Q1 and also Q2. So it is now new state. Q0 Q1 is a different state, Q0 Q1 Q2 is different state, and as it now we will see the transition of Q0 Q1 Q2. So Q0 Q1 Q2 on A, so just see transition table T. Q0 on A goes to Q0, Q1 on A goes to nothing and Q2 also nothing, so we will remain with Q0 only. Now coming to B, so Q0 on B goes to Q0 Q1 and Q1 goes to Q2 and Q2 doesn't go anywhere, so that is done. Now the last thing we have to do, in this transition table now Q0 is covered, Q0 Q1 is covered, Q0 Q1 Q2 is covered, and there is no new states formed after this. So this is the complete transition table that is actually for DFA. Now we have to know the initial and final states. So the initial states in that NFA will be the initial state, and the final state will be the state which is having the final symbol. So Q2 is the final symbol, so Q0 Q1 Q2 is the final state. Okay, the final state should contain the final state in its set. Okay, so there may be more than one final states. Now we will generate our this automata DFA from it. So this was an FA, and we are just now creating the DFA. Okay, so in DFA what we will do, we will create these three states, Q0 Q0 Q1 and the final state Q0 Q1 Q2. Now this is the final state, this is the primary state Q0, initial state. From Q0 now we have to see the transitions. So on A, Q0 remains to Q0 only. On B it goes to Q0 Q1. These two entries are done. Q0 Q1 on A goes to Q0. So on A goes to Q0, on B it goes to Q0 Q1 Q2. On B it goes to Q0 Q1 Q2. Now Q0 Q1 Q2 on A goes to Q0 only, and on B it remains here only. Okay, so in this way the things work. So now we have covered all the things in this transition table. From Q0 on A it goes to Q0, Q0 on A goes to Q0, on B it goes to Q0 Q1, on B it goes to Q0 Q1, then Q0 Q1 on A goes to this Q0, then on B it goes to Q0 Q1 Q2, then this goes to Q0 and on B on itself. Okay, so in this way we convert any NFA to any DFA. Okay, so what we have done in brief, we have taken an NFA like this. We have just created its transition table, and from this transition table we actually generated the transition table for DFA, which will have some different new states composing all the previous states in the some of the previous states in the NFA. Okay, so what are those previous states? If there is multiple transitions like Q0 Q1, we will consider it as a single state, and for each of the entry, the next entry will be of the state which are actually contained in these two, means contained in the entry only. So Q0 we have covered. Now there was number of this Q0 Q1, so we went to Q0 Q1. Now on A, where it will go? It will go to both of the states and see it will take the union of these two. So on A, Q0 goes to Q0, Q1 goes to nothing. So we will remain with Q0. So Q0 is here, same for this one also. And for this we have Q0, Q1. So Q0 goes to Q0, Q1, and Q1 goes to Q2. So we went for the union of this as Q0, Q1, Q2. Now this will be another state, Q0, Q1, Q2. We have covered Q0, we have not covered this one, so we will see how its transition work for Q0, Q1, Q2. So similarly, we have got Q0 and Q0, Q1, Q2, and we have created with the help of this. So this is all from my side today. So any doubt in this lecture? For this I have referred slide, so I will again go to some references. And someone asked for books, so I in last lecture I also told that you can follow Ahwalman City, so you can follow that. And if there is any question, so you can also write on discussion forums. Next week I will cover those also. So if there is any doubt, just comment. We have 3 more minutes. Okay, so quickly I am just telling what was the answer. So then we will wind up. So in first, the lexical analyzer reads the source code, is scan the code letter by letter. Okay, then there was a regular expression. So uh, means at least 2 ones should be there. So it was not able to produce all the outputs. That's why we have selected A. Then in third, there was given this machine 110. So on 1 then followed by any number of zeros should be there, so it is not following this, that's why B is the answer. Then there was fourth one, NFA may have epsilon transitions. Yes, in NFA if we have epsilon transitions, we just transit like if we are in state this, we can transit without any alphabet. Okay, with epsilon only, epsilon move. Okay, so transition are from states NFA, that is many. Then this is some doubtful case. Then there is 6 1. It generates the constituent strings of the language regular expression, which actually represents the language in a string form. Then there is a finite automata, which is implementation of regular expression, that is given in PPT only. And easier to implement, that is also given in PPT, that is GFA. Then there is regular expression, you just go to by converting this to decimal and just see divisible by 4 and minimum length is actually 2. Then there is lexeme. So lexeme is a sequence of character that defines a token, not any uh, different sequence of character. Then there is output tool lex, it may be covered next week. So it is actually output of this is a C program. Then these are some examples, and in this what we have got that a word which may have length 1, length 3, length 5 can be formed, that's why this is formed. Or word which one letter or one letter and 2 characters, or one letter or 4 characters, sorry, integers can be there. So for from there it can generate it, but it cannot be generated. So that is so 2 and 3 are the options answers. So thank you all, thank you for joining. If there is any doubt, just write in discussion forum and in this meeting. So thank you.